Okay, so thank you again, Behnaz, for your time to give a talk in the IEEE Task Force on Resilient and Secure Large-Scale Energy Systems, Internet Systems. So today we have a presentation by Dr. Behnaz Papari from Clemson University. The title of the talk is Holistic Performance Benchmarking in Power Systems with Distributed Control After Disruptive Cyberattacks. Just to introduce our speaker today, Dr. Papari received the Bachelor and Master in Electrical Engineering in 2008 and 2011 from universities in Iran, and then she did her PhD in ECE from Florida State University in 2018. And before joining Clemson earlier this year, she was an assistant professor at Texas A&M, and then before that, assistant professor of practice in University of North Carolina, Charlotte, where she taught at undergraduate and graduate levels. Again, Behnaz, thank you for your time, and the floor is yours.
I appreciate. Thank you so much for giving me this opportunity to, present the latest research that we have and we've conducted, after joining the Clemson University. Today, I'm going to present one of our recent studies that we went through the cyber physical system or cyber attacks with the application of the power system to increase the resiliency of the control system. And as you can see from the title, that the performance benchmarking power system would be one of our studies that we consider under the cyber attack scenarios, specifically for the distributed control system that we define for our application. The team that I'm working with here is good PhD students and master students and even undergrad that help us to provide the new concept around the control concept that for a long time I dedicated to. And I can say that my motivation to going this route, it was different reasons. And as you can see there these days, the modern power and energy system include some level of the automated control or even monitoring or health monitoring and the reason behind of that, because the day by day improving the technology and advance those technology bring some benefit, but of course some challenges too. And cyber physical security of the electronic technologies definitely brings those benefits associated with some challenges and poses some challenges for us to see that how we can keep our network, keep our control system still secure and also bring more resiliency to our system, power system or control system or physical category that we are looking for. So cyber physical security, or we call it CPS, studied from the different perspective. Could be from the hardware, could be from the communication point of view, could be from the software, and depends upon which angle you look at it, bring you a wide variety of challenges. And also, you need to know that how you look for the solution for your specific application corresponding to the different angle that look at that problem. And as I wanted to follow, because for a long time I work on the distributed controller system for the power system application, regardless of it's a ship system, regardless it's terrestrial, microgrid, smart cities associated with electrical vehicle. Control system or distributed control system include the several control devices, and as name show you that in a distributed fashion bring the resiliency and more reliability, of course bring more challenges because more communication network between the controllers. So controller devices became a prime target for the attackers. And is really worthwhile to look at in depth for the evaluating the control system under the cyber attack, to see that that level of distributed control that we offer the people, to show them that how increase the resiliency or reliability, can benchmark through the real real metrics, and also evaluating our control system. So understanding and quantifying the effect of the CPAS, cyber physical interruption, and also how we can accommodate those interruption or isolate it in a real time to evaluate our control system potential or vulnerability point is really matters. So it was the briefly in an introduction, several other studies went through it, and I'm trying to bring the new concept for the evaluating our control system by some sort of the benchmarking performance. And you can see, if you know that the types of the cyber attack that we have, as a well-known use is a false data injection type, or even controller hijacking or denial of service as a well-common use type of the cyber attack. How we would be able to model those attacks in the distributed control system that we designed for our application, and then how would be able to characterize the control system and benchmarking the performance of the control system associated with those aforementioned attacks is really what exactly I'm going to go through it today, and to see that how we would be able to bring another solution in a case that other researchers provide some control system, design control system, how we would be able to evaluate their control system under the attack. And there is some standard if we would be able to characterize their control system, then evaluate it. So physical system performance is arguably the most important criterion, which is come to the physical, cyber physical security. And the reason is because the electronic technologies and the other devices day by day have some update and make them vulnerable. And besides that, the benefit that bring to the equation. And goal of this study would be how we address the lack of an algorithm or method to benchmark the cyber physical performance of the power system, specifically in a real time. So we bring the MetaMetric concept for defining the performance criterion for our application. Later on, I talked about which system or which application I'm testing this methodology and how it works. But first, I'm going to talk about what exactly is what I mean by MetaMetrics. And MMM, I can say that is a performance benchmark method that adaptively aggregate the multiple metrics into the one criterion. And by capturing the property of each metric and performance of human decision maker would be able to make a final decision or final evaluation of our control system. How do you doing it? I explained it, several different metrics that we define and how we associate all of those metrics in a one criterion. As you can see it in a left side, the metric one, it was the power quality that we define it for the application, that total number of the load that we have. And then delta V is a voltage deviation measured in the terminal of each load. It could be one of the important metric that we can define it for our application. But it's not the only metric that we discuss it. So another metric is reliability. reliability. So as you can see in the formulation, the number of the out of service load or number of attack controllers or the total number of controllers bring us to the one metrics that we would be able to measure the reliability of our system. So what if we have two different metrics with the specific characteristic, and how we would be able to define the one comprehensive, the metric who defined very well each one of metric 1 and 2, and also evaluate our control performance, control system performance. And again, I say that we have a wide variety and list of the metrics. Another one, as you can see, is a resiliency metrics. And as the definition said that outage time and the critical outage limit that we have is defined to show the resiliency metrics. But we need the one holistic criterion to define all of each different metrics, and simultaneously in a one parameter shows us, not the two different or three different aspect metrics. The formulation that you can see at the end, the blue box, is the MetaMetrics that weighting all of those different metrics, and also all of the system measurements feed into it. At the end, decision maker preferences weight on the different aspect of each metrics and give you the specific one holistic criterion to evaluate your control system. Is the control system excellent or good or medium or a below average performance? And you can categorize your performance of the control system based on the MetaMetrics. So another point that I'm going to mention is the DM or decision maker. Decision maker preferences is really important because sometimes depends upon the objective functions. Decision maker or operator prefer to go less cost, more security, or depends upon the objective function, more clean or less loss. So their preferences is really matter to our calculation. And assumption is that decision maker is a non-exempt human who's the end user of the energy system, is the maximum things that we know about it. And then their preferences define in 4 different categories that implicit their opinions. And based on those, we weighting those opinions, we weighting algorithm assigned for per unit weight based on designated quaternions range for the decision maker opinions, and also other than relative performance of each metric with respect to the another one. As you can see from the table, we define that the 4 different category A, B, C, D, and based on these different weighting range, we would be able to show that, okay, the MetaMetrics measuring all of the metrics calculation and bring it to the range of the A, B, C, D. Then we would be able to see that, okay, our control system, distributed control system, perform very well or not, in average, or is below average, under attack. And the formulation, detail of the formulation, as you can see, it is in the blue, blue box. And by weighting the decision maker preference, we would be able to offer the unique benchmarking control performance. But again, I said that the type of attack is matter. Here, for this study, we would be able to model 3 different types of attacks: false data injection, controller hijacking, and denial of service. Every one of you may know about in the detail, and most probably for some control designer, controller hijacking is one of the most important because completely hijack the whole control system. But fortunately, because distributed fashion bring more resiliency, then if we would be able to measure the control performance and evaluate the performance of the control system after attack, after one or several of those controller hijack, we would be able to catch the sensitivity of the control system that designed by the designer. So I can say that different type of attack based on their characteristic need to model to see that which type of attacks bring more impact for your control system, and also which type of attacks together bring more disaster for the control system. So by those goals, we decided to go and implement our methodology in one of the applications, which is the ship system, Navy ship power system for naval vessel. And as you can see that Navy ship power system has a special level of the focus from the cyber physical security or CPES concept. And the reason because these gigantic DC microgrids is on top of the ocean and count as islanded microgrid, and you are not able to support them from the shore when they are in the middle of the nowhere, and so it's really matter to evaluate the control system, distributed control system that designed for that ship system, and to see that how we would be able to evaluate resiliency index for that application. And most probably the threat, cyber threat, is the most attack for them and make them one of the good candidates because they are islanded from the rest of the system, and smart metering or does not lack of those monitoring from the rest of network make them one of the potential point of the attack. And as you can see it here from the picture, we picked one of the 4-zone ship power system as our case study, and then trying to evaluate the distributed control that we designed for the ship system by MetaMetrics to get the benchmarking performance and to see that how the control system that we distributedly designed for the ship power system, perform during the attack when we're modeling the false data injection, controller hijacking, denial of service, or several of them together. And by choosing that case study and several consideration and assumption, we decided to go pick one of the main part and component of ship system, then focus on that area, which is the generator. As you can see from the previous picture, the 4-zone ship power system include 5 different generators, 3 main generator and 2 auxiliary one. And each generator, which is the 100 megawatt ship system, and each generators would be dual winding machine. So we have to define 2 different controller as A and B for each generator, regardless is the main or auxiliary. As you can see in the graph, we define that the distributed controller for the 5 different generator and main and auxiliary generator, and because they are dual winding, and we have to dedicate 2 for each one of them. In total, we have 10 different controllers who communicating with each other and then sharing the power and reach to the consensus point. After that, they sharing the power between each other. So what if we have an attack in one of these chains, regardless, false data injection, controller hijacking, or denial of service? What happened for it, and how the rest of control system distributedly would be able to catch up with the rest, and how long it takes? Resiliency metrics, reliability metrics, and power quality was the metrics that we defined to evaluate our control system. We leverage our model that we had from the ESRDC library as a ship power system and model it as a physical system in the O polarity as a real-time simulator, and also leveraging the national instrument SPRIOS for controller, and then finish our control hardware in the loop instantiation, and by running the model in a real time, controlling real controllers in a real time, getting the data in a real time, then send it to the MetaMetrics. And to see that MetaMetrics how measuring and collecting all of the measure data, and also gave us the decision maker preferences, tune, at the end, evaluate and benchmarking the or categorizing our control system performances. So the case study that we went through it was the different cyber attacks, and I can say that how we define two different surface and also the vectors. Attack is the surfaces that are controller program. Basically, controller program is the surface of the attack. They're attacking at that point for the changing the code for the false data, or measuring the voltage or current from the generators that they are going to share with each other, or even the power sharing amount between the agent could be the surface that attacker attack that. And vector, attack vector is the malicious viruses that introduce the system via the human machine interface, HMI. And by those consideration, we defined different case studies for the 4-zone ship power system with the 5 generators that controlled by 10 controllers. What if one of the controllers that associated with the 1A part of the generator 1 be under attack, or even 2 of them under attack associated with the one other agent who with the generator 3, in other zone be under attack. So the table shows you that the cyber attack progression that for the 5 minutes interval that we define for the system under different type of attacks, under different location of the attack on the 4-zone ship power system. Then HMI as a central computer in a ship, local area network, connected to the controllers to need some picture or evaluation of the whole control system of ship power system to be able to rank the control system performance. Is a good still after 1 attack happen, or after 3 different attacks happen, is the below average the performance of the computer system. So we're trying to find that, or benchmarking the control system evaluation to see that how our control system that we design is the resistance under the attack, and how would be able to time-wise through the resiliency metrics would be able to back and remedy out of this situation. So the case studies that we define for those attacks would be the false data injection, controller hijacking, we call it hide, and denial of service. Consider with the bus voltage impact. As you can see it from the graph on the left on the top, the transient voltage side at 300 seconds, as you can see it here, at a 300 seconds, when the first attack happened, false data injection and hijacking are introduced, then voltage re-stabilizes it into the previous steady state version until the other one go. And also for the denial of service attack scenario, a 10% transient overshoot you will see and follow by sustained 4.5% steady state error in a aftermath of the first attack. So by those case study, we're trying to find that, okay, how distributed control treat after those attacks and evaluate it. During the first false data injection and hijacking attack, for approximately 10 seconds, M as a metric drop below the initial value of 65% score, which bouncing back to settling around 70%. as you can see from that. M as a main parameter that in a MetaMetrics methodology we define it, resettle at the higher level than the initial score, and includes the factor of the number of attack detected. Need to understand it first, how many attacks we face with it. And also there is more information that included in that concept as a M, differences in the transient magnitude and settling time under different cyber attack scenarios is also represented in M. An important takeaway is here that MetaMetrics analysis enable decision maker to observe several measurements in a one holistic criterion as a MetaMetrics with a different angle, with a different, challenging point, not only one type of attack, several times and even different time. So it makes us more comfortable to see that, okay, with this concept, we still would be able to evaluate our control system with a wide variety of metrics, wide variety of tune, and also see that how resilient our distributed control system that we design is. And I'm sorry. This would be one of the main concepts that we went through for this study to show that every one of the control designer would be able to test their control system performance by the benchmarking and evaluate their system to see that what is their vulnerable point and what exactly is the sensitivity of that control system as a baseline, how they would be able to improve it in a specific time. Consider a different time of attacks and different types of attack. And this would be main contribution that we so far went through it. And I can say that this study demonstrated a new approach for the benchmarking, and we are going to go extend this work along with the rest of the, previous knowledge that we have from the distributed fashion control, and equipped our methodology with the more faster detection attack, because I can say that until the point that we won't be able to detect the attack accurately, it would be able to, provide us more accurate measurement from the evaluating the control system. And I can say the key property of the proposed method for the MetaMetrics was the generating one holistic performance criterion, define a variety of the metrics, not only one aspect, and incorporation with the human-machine interface and preferences, their opinion, and picturize the control system to the operator that how they would be able to manage after attack, the rest of the system. And MetaMetric was tested for the 4-zone ship power system, is the potential to extend it for the 6 zones ship system, or even the other type of application in a large scale with the time sensitivity. And I try to using the MetaMetrics as a reference to improve the control architecture, or control design, integrated control program, to mitigate the impact of the cyber attack and reserve it for the future generation of the ship power system that Navy going after. And I can say that one of the most important point for us right now is that how we would be able to add the detection attack to this concept and then make it the one comprehensive evaluation benchmark for the any type of control system that designer design it for the, I mentioned it with the focus of distributed control system for different application in a large scale, and even in a manner that, they would be able to reach to the one standard and for the that which work for the several type of the application. It was pretty much about I wanted to cover for today's presentation, and I really appreciate the audience. In case of the I give a time to the questions, comment, and even discussion.
Thank you, Behnaz, again for your time and the very nice and on point and on time presentation. So, any questions from the audience? You can unmute yourself and ask or write it on the chat. I have also a question, but let's wait and see.
Sure.
Okay, maybe I go first. So, I mean, the question I have is Juan and I, who is also in the participants, we work in the past on something similar using Choquette integral, which is pretty much the concept of, again, aggregating different combinations of criteria in order to define a function that can be used for different purposes, whether you focus on reliability, resiliency, on security. So and I'm sure there are other kind of quantitative methods, right? That you can set up different weight factors or fuzzy measures in order to combine different quantitative metrics. So how different, or how you define those factors in MetaMetric to allow different weights or expertise input, or let's say stability input like voltage or frequency into the calculation of the metric.
Actually, it was one of the really good point that you mentioned it, that, and we think about it a lot to see that, because every controller designer, okay, think about their specific approach and also a specific angle that look at the problem. So the variety of the metrics would be really different, and parameters that they involve, how we would be able to define one comprehensive MetaMetrics with the proper weighting on each metric is really challenging. And recently we decided to go with some sort of the AI-based type of the learning to analyze the historical data of the the control system and data that measure from different angle, for instance a stability point, to get the pattern and tendency to see that how we would be able to update our weighting factor in MetaMetrics more intelligently based on the train process over the time that we get from the operators' preferences. We get with the different opinion in even operators and different type of the preferences. Sometimes I said that with the different type of the objective function, definitely each metrics have a different priority, different weighting. Some people said that, okay, stability is much more important, as a one metric for me compared with the cost objective function. Or even, in a ship system, someone said that, okay, the loss, power loss is really matter. And we're trying to find that a way that leveraging basically some sort of the deep learning to would be able to automatically update the weighting based on the data that we get from the different type of the preferences from the specific objective function that operators or the people define as a main objective, and they put the rest of the metrics as a second level objectives for them. And in this way, still work on it, I can say that, because it's really hard to fulfill everyone and make every angle satisfaction. Definitely we need to sacrifice something based on the other option or other metrics, but updating the weighting factor from, for instance, different operation mode, cruise operation mode or battle mode is really challenging, because even the time horizon for those is really different, and those factors make us to little work on depth on it. Okay, I really want that to fulfill the most possible scenarios for the wide variety of metrics, but definitely will not work for the every aspect. We need to ranking them. Priority table defined for the R metrics is matter, depends upon that operator what exactly, or HMI what exactly request in a different operation mode even.
Thank you, Behnaz. So it's update, right? It's important, objective functions. And then I would say it's also physics of the system play matter on how do you decide on different
Yes, definitely
aspects.
physical layer as the one that we model is matter, because even the hardware that we have in a physical layer is really, really important for us, because sometimes that one not helping us to even go further. And in a case that those hardware under attack, then make us more problematic compared with that and make the scenarios more complicated for us.
Okay. Yes, I understand. So there is a question from Yanis Zorafopoulos. So what are your threat model assumptions? For instance, how do you know that the measurement reported, right, for the calculation, I assume for MetaMetric value, are not manipulated to deceive those metrics?
It's a really a good question, because it was another aspect that we decided to go and put us in a route that go for the good detection process, because we assume that under attack, and and we trying to model those attacks by ourselves, but the methodology that we need, we need to define it to first basically to first evaluate the signals that come into the controller or out of the controller, and then process it. How healthy is our signal in or out of the controller, and how is the different in or out signal from each controller, and what exactly we look for it right now to see that, okay, we consider the attack, we assume that we had is interpolated. Definitely we know it that, okay. But another step would be that when we offer the signal and no one knows about the point of attack even, we need to look for those attack, interpolation of the attack to figure it out, and some sort of the pre-processing to purify our control signals in and out of the controller, then led to the rest of system in a healthy condition go for their aspect. And I can say that this question bring more challenge, for us. And when we detect one of the controllers is under attack, because it's a distributed manner, how we isolate that part of distributed controllers with the rest of system, and how fast we would be able to bring this system back to the rest of system, health system, it would be the really, really challenging, specifically for the application like a ship system. Ship power system, time horizon is different, and in a physical layer, power electronic layer sometimes make it super hard. I'm not talking about only system level.
Yeah. So thank you, Behnaz. So Yanis has another question, but before asking, maybe there is another question from the audience.
I need to check.
No, okay, no other questions. So let me ask you this question from Yanis, and I assume will be the last one if no one else has any other questions. So how many Byzantine nodes could your distributed system in terms of consensus withstand? And then if it has two questions, like post-detection, how you can rejuvenate those compromised agents.
Okay, I can say that for this system, we tested our benchmarking performance system for the 10 nodes. And a scale definitely will increase, and right now we are working on it for even the terrestrial microgrid with the PV farm. In a case that we have attack for those systems, how we would be able to, in a large scale, be catching those attacks and also evaluate our control system performance. And I can say that scalability is really matter when we are talking about real time, when we are talking about the time horizon, that is the below the millisecond, and make it really challenging. And I'm not sure about, because not tested yet, to see that distributed control that we designed, how would be successful, stay in a good category and class for the benchmarking. And we will see in the future. And the second question was about, I keep forgetting it, what was?
It was about post-detection, like how you can rejuvenate the compromised agents, right? How would you be able to restore them?
Yeah, and another one that we trying to find the type of the, we call it the spare type or reconfiguration for the control system, especially, how we would be able to reconfigure the distributed control agent for some agents that is under attack and takes longer time to would be able to bring them, or even not at all safe to bring them to the network. We're trying to define some sort of reconfiguration with the other controllers to bring it to the loop, and then as a healthy control system, kick them back to get dedicated to do their unhealthy, controller system by reconfiguration. I can say that reconfiguration for the ship power system, because not have too many options, as a spare, it would be a little challenging. But in a case that we find that, we define it in an algorithm like that, in a case that we're not finding any type of the healthy reconfiguration path for those part of network, we prefer to go to the load shedding or temporary load shedding for the, less priority type of loads to would be able to survive until the past attack period. And then when we go to the normal operation mode, thinking about how we would be able those under attack system back and make them healthy.
Thank you, Behnaz. So I think with that, we can.
I have one.
Yes, Juan, please go ahead.
That I was. I would like to know, because like Harry said, we are also working on something that is close to kind of doing a combination. So I would like to know, how do you handle the combination of sum of values that, for example, the best value for some of them could be 1, but then some other one, the best value could be 0, right? So they're like different, and you cannot use the same, like, yes, from 0 to 1. So how are you handling that?
Actually, the table priority that defined by the mission operator is the matter that how we go to that route. And based on the priority table, we define those priority for those measurements. And I can say that they call it vital and non-vital characteristic and organ metrics. And is totally under the HMI. And based on what they want, okay, is like they have a more monitoring history between controller and them. And so they know that over the long time, what exactly is the most important vital parameter for them, okay? Stability is the best for them that they look for it or look after it or not. Power loss in physical is really matter for the inverter with a 30 megawatt is matter, even blowing the physical system in some part. So in the part of work that we follow, we definitely follow that HMI priority table, what they asking for. But algorithm would be able that, to play with the weighting. We try to look for that some sort of learning time, AI-based type, learning algorithm to update our weighting, not only based on the HMI of preference or opinions, based on the what exactly currently in a real-time system needs for it, based on what exactly physical system dictate to us, and give a better sense of our physical system instead of only listening to the one that on the top said that priority is that one, and gave the balance between physical system needs at that point, at that time that attack happened, and also priority table that HMI requests for, something in balance.
Okay, perfect. Thank you. And one last one. The values that you are getting, you are getting those values for the entire system, or you can also get values for a specific nodes or buses? Because, for example, a stability for the entire systems, I mean, could be somewhat good or medium, but maybe at one particular node, the stability value could be bad or could be
yes.
So.
The one that, it was really good question, the one that for the general system, for the whole system.
Okay.
In a depth, I can say that if we are going to go for the specific type of the component to see that a stability for that generator, a stability for that converter in a chip system is good, make a lot of in-depth assumption and consumption, and and really go through the sensitivity analysis of the discussion. It's the out of, I can say that is related to control system evaluation, but it's not the route that we went through yet. Okay, in a specific component, that micro component or micro component type, if we're going to evaluate the control system or controller evaluation for the controller performance for each controller to see that, okay, they are good or bad, put us in a sensitivity analysis, and is the something that not yet covered for this work in this study.
Okay.
And it's really interesting point, because for a generator like a 30 megawatt generator, definitely is really matter. We are not talking about 1 megawatt, we are not talking about kilowatt, because we have 30 megawatt, and that definitely gave us more data about even the sensitivity point of our control system that really vulnerable to the attack from the attacker, and provide that information for us.
Okay, perfect. Thank you.
You're very welcome.
Thank you, Juan. Thank you, Behnaz. So with that, I think we're good on as we planned, 40 minutes plus 10, around 10 Q&A. Yeah, we went exactly on time. So let me thank you again for your time, Behnaz, and for the very interesting presentation. We as we said, we're recording. We're also gonna post it on our website. Thank you, everyone, for participating on Friday. And I wish you a very good rest of your day. Yep. Happy Friday to all.
It was my pleasure. Thank you for this opportunity that presenting, the research, and thank you, everyone, audience, and have a great Friday and weekend.
Thank you, Behnaz. Bye-bye, everyone.
Bye.
Thank you very much. Bye.
Bye-bye.